works. And it's really second year, or maybe you do it in third year, I'm not quite sure, in the American system, of optics, okay? So I have optical angular momentum, and it's transferred to a wave plate. So you remember that if you have birefringent particle, it will have two refractive indices. Different refractive index in x direction and in y direction. And so if it will be particular thickness, if it will be lambda over 4 thick, then if I put the linearly polarized light in 45 degrees angle onto a plate like that, then on the outcome I will have circularly polarized light. So this is basically what I'm showing you here. So I start with elliptically polarized light because it's more general form. It's incident onto some sort of birefringent material, and it can be described with this equation. So I have my electromagnetic wave, this harmonic wave, and the two components here, okay? And then it passes through the material. So I have fast axis here, and I have the plane of polarization, and that's angle theta, phi between them, and I have fast axis of the lambda over 4 plate on my birefringent material, and optics axis of the trapped calcite particle. And so on the outcome, when it travels through the material, it had traveled distance d. So I had exponential I alpha x, and now I have, sorry, kx, and now I have I k d, extraordinary and the ordinary part here. So these are the extraordinary and ordinary refractive indices, right, which are different. And as you know, in calcite, for example, the extraordinary and ordinary refractive indices are very different, and so therefore I'll have big difference between these two components. Okay, and so if I have a plane wave, the total angular momentum of the field will be expressed by this expression here. So the angular momentum densities of the field before L0 and after L can be determined by these two expressions, okay? And so I have this difference between refractive indices here, and this will determine what's happening to my wave. So if I look at the change in angular momentum of the light, which results from the torque per unit area of this birefringent particle, this is the expression. Okay, and it has two terms, and this will be alignment term, and this will be rotational term. So if I make this alignment term 0, then I'll have proper rotation. Otherwise, if I make this 0, then I will have just the alignment term present, and I'll be able to turn the particle to my right. Okay, so you can use that. You can use it for dreaming about optically driven micromachines. So the idea here is to start with what we did, is that we took a birefringent particle of just crushed calcite crystal. So this is my calcite crystal. I put it into the beam of highly focused beam of light. It rotates. Then I build a silicon dioxide cog, and I put them together, and I make the machine turn. Okay, so this is the turning of the machine. So this is my calcite particle, which is spinning, presumably round enough so you cannot see that it's spinning, and this is my cog, and the cog is not fastened, so it just follows the flow basically, and it's touching with the cogs, it's touching the rotating particle. And then I can take this one. Will it go? Yeah, it goes here. So I have now two tweezers. This one is trapped in linearly polarized light, and even if it would be trapped in circularly polarized light, it's not birefringent because it's silicon dioxide, and so it's just plainly trapped. I bring the particle in, and when the particle is spinning, the cog will spin around it. And then by sheer accident, we also had a one-axle machine. So there is a big shard of calcite crystal on top of the cog. In actual fact, I was just trying to shake it off. But then I realized afterwards that it looks like a good machine. on one axle. So again, this is not very clever building of machines because this fellow cannot rotate on its own at all. This is all based upon the fact that this little rotor is birefringent, and then I bring it close to the structure that I built. Okay, so transfer of angular momentum of light now. So we switch gears. So that was with birefringent particles, and now what we do is that we are saying, let me back up a little bit. These were not very intelligent machines, so, and not much could be done with them apart from having fun and publishing a paper. So what we wanted to do is to try to establish methods for production of birefringent particles which will be of a given size and of a given shape. So what we wanted is that if you really want to do measurements of optical torque, you want to know the shape of it, and the simplest of shapes is spherical, because then the equations are very simple. So the idea was, let's produce spherical particles and then see how we will use them for production of machines later. So we, in colloidal solutions, started to produce spherical particles. So this is optical image of the spherical particle. And we also, in same solutions, could produce particles like this. So if I back up, there is the particle which is rotating. So this is calcium carbonate, calcite, and it's made in the solution, and it rotates, but it's just this very elegantly looking thing, and it's definitely birefringent, but it cannot be used for, well, it can, but it's not as good as having it spherical.
What's the size of that last particle?
Of this?
The previous one, the calcium.
About 10 microns. Okay, but we had them smaller as well. Okay, so here we produce spherical particles in colloidal solutions, and this is the optical image of it, and this is a scanning electron micrograph of the particle, and you can see that it looks pretty spherical. And it's better as probe particle, that we can achieve smooth rotation and we can trap it three-dimensionally. Okay. Now, the thing is that there is surprising material science in it, and it is because this is calcium carbonate, and it's about, so this is micron size here, so you can see that it's 5 microns in size. So it's huge. It cannot be a single crystal. Okay, and single crystal of this is a form of calcium carbonate which is called vaterite. So it's different from this one, so the crystal structure of it is slightly different. It's negative crystal. And the thing is that it's quite surprising that it can crystallize in spherical form. Because the single crystal obviously is not spherical. So we were asking ourselves, how come that they are spherical? So there's I'm going a little bit on a tangent, but it was interesting, a little bit of interest in materials construction. Okay, so we did XRD, and we found out that it definitely is calcium carbonate. So it's definitely the material that we thought it would be. Okay, so the question is, and because we can rotate it with circularly polarized light, it must be birefringent. So how come, so there are several questions. How come that it can crystallize as a sphere? Secondly, how come that it can crystallize in such a way that its birefringence is maintained, or to a large extent it's maintained? Okay, so we started to read a little bit about it, and we found out that there has been a lot of work done on calcium carbonate. All of those crystals here are rather large, but you can see that when they start crystallizing, you can see that they start as little rods, and then they can look like this, and they can look like sheath of wheat, like so, and then eventually they are round. So it's quite a surprising stuff happening there. So we were thinking that maybe this is something what we experience as well. Maybe that's how it happens. And you can see that when crystallization takes place, so this is pretty old paper here, so the sort of single crystals build a line, and then they build this sheath of wheat, and then somehow they are bunched in the middle, and then they sort of bunch out again. And somehow they continued that way. So, this is not right. I'm sorry, I have wrong stuff here. Okay. I don't want this. I have to move it on. Oh, yeah. Sorry, okay. So, again, few scanning electromicrographs. So this is what we were producing. So we were producing quite nice looking crystals, but we were producing also some sort of funny looking shapes as well. And you can see this is calcite and vaterite. So these are calcium carbonates in two different forms, crystalline forms. And so calcite will crystallize like so, but vaterite will crystallize as little balls, which we have. And we could see the same thing, so this is not our figure. This is how it's made, and we do say a little bit of voodoo is needed to get them spherical. We say that because we have had a lot of interest in our spherical particles, and people were trying to follow our fantastic recipe from our papers, and very seldom can they build spherical particles, and I have a couple of students who can do it. So there is a voodoo involved. We had also friends in other laboratories who said if you use very clean water, you won't be able to have spherical particles, but if you use bad water, you might be. So the question is how the nucleation of those particles takes place to start with. And it could be that you need a tiny little particle, whether it's calcite or something else, and around that you start building that structure. Now they are very curious, so this is one of those particles. Looks pretty spherical, and it doesn't want to rotate. Yes, it does rotate. And it's three-dimensionally trapped. And what we can do is that we can put two linear polarizers, so polarizer and analyzer, and we can look at the structure of it. And this, if you can trap this particle, you can see this is trapped now, and you can see that this is the sort of different types of polarization that you can see in this particle. And the question is, how come that it looks like that? And you can build models which will show you how it all occurs. So here is the model. So we are taking vaterite rotating between two cross polarizers, and you can see that depending on the diameter of these particles, we will get in the two cross polarizers, we will get different intensity profiles. And if you model it again for even bigger particles, these are the structures that you will get. So you can see that if we go to our experimental results, this is what we are seeing. Okay. Now the other curious thing is, I don't know what I have done with the order of my slides, is that if you were to measure how birefringent it is, and we have done that, it is about 0.8, so 80% birefringent in comparison with single crystal. So that's pretty much. And so it shows that our particles somehow maintain optics axis and optical properties very close to the single crystals. So what can we do with it? Well, we can, as I said, we can use it for measuring viscosity in very small volumes of a liquid, or even viscoelasticity, which I will show you tomorrow. And so basically, basic idea is something like this. I take circularly polarized light, which carries h bar per photon of spin angular momentum. I have my perfect lambda over 4 plate, which I create. I let the light go through this lambda over 4 plate. It starts rotating in opposite sense to this one. And then I can see that I can have zero light or whatever light in the transmitted light. I won't go to this detail here, I'll tell you more about it tomorrow, but basically if you are able, if you know everything you need to know about the light coming in, if you know the size of the particle here, you can then look in the transmitted light, measure the change of the polarization, and then the only unknown, will be viscosity of the liquid in which it rotates. Now, people have measured microviscosity using optical tweezers. What they have been doing is to take a trapped particle and oscillate it in the liquid. But in order to do that, you need quite a lot of space for doing it. So if, for example, you were wanting to measure viscosity inside a cell, or viscosity of very tiny amount of liquid, oscillation in x direction would be much more difficult to do than just rotation in very, very small volume. Okay, so how do we do it? So I have my circularly polarized light, it comes onto the particle turns around in optical tweezers, and then change in polarization takes place. So if I know the power of an incoming light, and I can measure here, so this is my incoming light here, and I measure the transmitted light, circularly polarized, left-handed and right-handed, and see what the difference is here. I have my degree of polarization of the transmitted light. I'm assuming here that all the light which is coming in is coming through the particle is detected. So no light escapes here. So I can really measure that difference in the polarization here. Okay, so my light comes in, it goes to lambda over 4 plate, goes to the beam splitter, which is polarizing beam splitter, goes to 2 detectors. So this detector looks at left-handed and this one looks at right-handed polarized light. Angular momentum flux is this change of polarization times power divided by omega. And then I have optically applied torque, then is the change of polarization times incoming power divided by optical frequency, which I of course know. And then I'm in the liquid, so I have drag torque. And drag torque now is given by the viscosity of the liquid. The sphere's radius to the power of 3 times frequency of rotation. And obviously, frequency of rotation I can measure very easily. So, if I do that, what happened here? I'm not sure. I pushed the button the wrong way, I think. If I do that, then I can now determine viscosity. So what do I need to know? I need to know the size of my particle. I need to know the frequency of rotation. I know omega, and I measure the change in polarization, and I have to be able to measure the power of the incoming light and know the efficiency of the high numerical aperture objective, obviously. But that has been done. So this is how we do it practically. So now what we have neodymium ion laser. I shape my beam so that I can overfill or just fill the objective. Okay, then I go to my sample. Then I have a condenser. I can collect all the light here, transmitted light. I put it on the mirror, come in here, leak a little bit of light to be able to measure the signal here, and then quarter wave plate, 2 detectors, beam splitter and 2 detectors. So this is left-handed, right-handed polarized light. Okay, and here that will enable me to measure the particle, how it's rotating. Okay, so rotation of the particle, okay, in time, and then left-handed and right-handed circularly polarized light. I take the difference between them. I know what power in the beam I had, incoming beam I had, so I can make my calculation now. Okay, so as I said, I repeat, this is real signal. So here the rotation is 110 Hertz times 2 pi. Okay, and basically circularly polarized light, optics axis here, polarizer here, detector here, and we have measured that. So this particle acts as wave plate, and then I have elliptically polarized light, or if I have linearly polarized light, rotation can be determined too. Okay, so here's the rotation, so we have to check that it actually works. So there is not so spherical particle, but you can see from the shadow here that the liquid is turning around, its particle is rotating. It's pure water. We measure the viscosity using the method that I described to you before, and it agrees within 3%. So this is for purely viscous liquids. It's a pretty good method. Okay, so we check it again. So we measure the glycerol. Why did we do glycerol? Well, basically because the viscosity of glycerol is very well documented and at certain temperatures. So we have done the measurements and then we have compared it with accepted glycerol viscosity data. And you can see that it agrees pretty well. Now, if this is what I was telling you about, and somehow displaced this slide. So this is quite a surprising result, as I was telling you before. I want to characterize this vaterite using optical tweezers. So here I have my vaterite diameter. When I told you that we can make them in controlled way, this is a little bit of lie, a little bit of lie. So we make them first, and then we look what sizes we got. We do know that if we, the shorter the process is, the smaller they are, and then they can grow to certain sizes, and then they don't look that good. So it's a little bit of luck there, but if you make enough of it, you can find particles with different sizes which look pretty round. Okay, so if I had pure single crystal, this would be the something happened here again. Torque efficiency. Which I have for certain vaterite diameters. If it was pure calcium carbonate in vaterite structure, then I would have this dotted curve here. And here I'm plotting the results that we got from our measurements. So, and then a hyperbolic model that we have applied, you can see that the results are very good. So you can see that pure vaterite has refractive indices which differ by 0.1, and our vaterite has refractive index, our spherulites, our refractive index is about 0.09. So the spherulites are 0.06. So you can see that we can follow it quite well in size as well, and see that the maintaining the birefringence is pretty good. Okay, so what else can you do with it? Well, you can pretend to do biology with it. Okay, so what you see here is our first attempt of measuring, artificially measuring in artificial liposome, which is about 15 microns in diameter, putting vaterite into it and measuring or building artificial liposome around the vaterite, and then measuring the viscosity of the liquid in the vaterite. And so, in principle, so that the rotation takes place, you can see, because you can see the movement of the liquid inside. And if I slow down, you can also see that the inside particle rotates. And then you can see a little bit of changes in the polarization here because of the rotation. So you can determine the viscosity of the liquid inside. And then sometimes when you build artificial liposome, you not only have one vaterite inside, but many, but unfortunately this film doesn't want to play. Okay, so then you can start saying, okay, well now I can build my optically driven micromachines. So this is first attempt of no good optically driven micromachine. I mean, it's pretty cute, but you can't do much with it. So basically what you're seeing here is a trapped vaterite and a free vaterite. And as the vaterite is rotating, you can see that the other particle is drawn into the field of the first one, and they rotate together. So they are machines, but they're not very good. But what you could do is to trap two vaterites. So I have double trap here, and I trap one of the vaterites is spinning in one direction, and the other one is spinning in the other direction. And what you could see was happening is that the particle was rather far away, and you could bring it into between these particles. Well, that's not a particularly useful machine either, but if you can imagine now that you could trap in optical tweezers in a row of optical tweezers, build a channel like so with optical tweezers spinning, each side spinning in a given direction, then you could lead this particle through the channel between them. And in fact, This is what people have done. So this is work by Jonathan Leach and Mark Stargett. They are using our vaterite particles here, and they have a little channel here, and then you can draw the liquid between those channels, and you can visualize the fields of the liquid. So this is real stuff, real optically driven stuff. Okay, what else can you do with it? Well, as I said, what it is supposed to be good for is that if you have very, very, very small amounts of liquid, microliter or less, you can still use this method for measuring viscosity. And you could wonder, what is it good for? Why is it interesting? So, for example, we have been collaborating with people who are interested in so-called dry eye condition. So what it means is that when you blink, there is not enough liquid in your eye, so that it's very painful when you blink. And it's due to the fact that this lubricating liquid is missing, basically. Or it's there, but it doesn't fulfill its function. And the idea is that when this condition occurs, the viscosity of the liquid changes dramatically. And if you were able to measure the viscosity on very, very small amounts of that liquid, then it would help to diagnose the illness. So we thought, oh, we will do it. So we had a very devoted student who took he had what do you call contact lenses, and this is a dish, the contact lens here, and we just dropped the vaterite into it, and then we're rotating it here. It doesn't play very well, but you can see rotation a little bit and then it breaks. But believe me that this particle rotates quite well, and by measuring the rotation and polarization changes, you can measure the viscosity of the liquid, and very small changes in the liquid. Now the other thing which you could do is to measure intercellular fluid in picoliter amounts. So what we did here is we have a macrophage here, and we used laser scissors, which were blue, which was blue laser. We were going to punch a hole in the membrane of the cell. What we instead did was to burn the cell. So we constructed a big bleb which has liquid in it, cellular liquid or intercellular liquid, so we can pretend that we are doing good stuff. So now what we do is we have a membrane here around this bleb, and we punch a hole in this membrane using blue laser. Then using red laser, we put the particle inside that bleb, and then we adjust our polarization state, and we rotate this particle inside. So this is birefringent particle, and we rotate it inside the cell. So here it comes. It's going in, and it's almost in now. Now it's totally in, and you can see the rings around it, and now it's rotating inside the cell. And obviously, through the same measurement that we did before, we can measure the intracellular liquid's viscosity, and it's not that different from water, so it's not incredibly interesting, and it's not inside the cell. It would be really great if it would be inside the cell, but unfortunately, it's just the burned bleb of the cell. Okay, so then, what we thought we would do here, actually we didn't think of it, but our friends from Irvine in California thought of it. They were looking at transduction, signal transduction in cells. So we have a cell here, and we look at the Mechano transductions of the cell. Earlier, what they have done is to take linear tweezers, so tweezers where you transfer only linear momentum, and they were bringing it close to the cell, and then they were looking at the reaction of the cell, how the signal was transducted, using fret and flint. And they were able to follow the signal throughout the entire cell. And then the question arose that it is interesting not only to look at, if you nudge the cell, you introduce stress on the cell, which is linear, because in many more applications in biology, what you really are interested in is shear stress. If you want to do the express shear stress on the cell, then you basically have to have some sort of stuff rotating around it to be able to do so. So here are our vaterites, and we put them into the solution where the cell is sitting on the bottom of the slide, and we bring the vaterite close to the cell, but the vaterite is not touching the cell. So the linear momentum is not, so the linear stress is not being applied to the cell. And so we rotate this and see what happens. So let me see whether we can see what happens. So you cannot see anything. That's a bit sad. Okay, well, I was sort of prepared for it. So here we go. So what happened here was that the vaterite was sitting, as is indicated here, and the cell migrated away from the stress, shear stress, and the signal is within the cell. This is fluorescent signal, was changing as well. And it was very obvious that it was happening because of the vaterite rotating, because firstly we could stop the rotation and the cell came back to its original position. Secondly, it wasn't the laser influencing it, because, as I said, if the particle wasn't rotating, the cell was happily sitting where it was. So, yeah, so it can be used for studying Mechano transduction in the cell. How am I going for time? I have a few minutes more. Okay, so let me now switch gears a little bit and start telling you about optical angular momentum transfer when using orbital angular momentum. So today I will only have time to tell you how we produce the beams which carry orbital angular momentum. So normally we have Gaussian beam, and we said it can be linearly polarized or it can be circularly polarized. And if it's circularly polarized, as we said, we can transfer spin angular momentum. But on the other hand, we can produce beams which are called optical vortices or singular beams or Gauss-Laguerre beams of light, which look like this. So if we look at the profile, intensity profile, what's characteristic for those beams is that they have a ring of intensity, and in the middle they have what is called singularity, which comes from the fact that there is space singularity in the middle here, and in the intensity profile, the intensity goes to zero. They have, so these beams, it's not just a donut beam, but it's a beam which has pointing vector, which is like a spiral, and angular momentum of it will be integer times h bar per photon. And it has phase singularity on axis, which is the dark spot. It is can be generated by lasers. If you have a spot on the output mirror of the laser, you can do it. Or you can have a phase plate or hologram, SLM, or whatever you want to have in order to produce different Gauss-Laguerre beams of light. Like Gauss-Laguerre beams of light are orthogonal model solutions of scalar paraxial wave equation, and they look something like this. And these are the different parts of it, and the most important is this part which I'm showing you here, where you can see that from the Gaussian beam, depending on the indices L and P, we can create this Gauss-Laguerre beams of light where we have always singularity in the middle. And as we go to higher and higher L values, the hole in the middle, if you wish, is getting greater and greater, and the ring of intensity of light is getting narrower and narrower. So this is how the solutions look like, and then we are not interested in the ones which have the P here different from zero, so we take them out, and we only look at the donut beams because they are easier to treat and more usable for what we want to do. And if L here, so this is L here, okay, if L is not equal to zero, we have helical wavefronts. So, so the angular momentum eigenmode is LH bar, as I said. So phase singularity in the middle. Okay, so this is how they look. Okay, so if it's L equal 1, this is how it looks. L equal 3, we have the 3 spirals like so, and then we have the angular momentum. And we can go further and further up, and people have gone to, I'll show you examples of LG060, but here is how we build them up. And what you can see here is that this hole in the middle is getting greater and greater, but we have more and more orbital angular momentum that these beams carry. So it's 50 h-bar per photon of this one. And if we go one more, we forget about it, and then you can see this is one example. Let me back up. So what it is to be noticed here, we have two Gauss-Laguerre beams of light, one going one way and one going the other way. And they have, so this is L equals 60, and this is L equal 20, I think, or 30 or something of the sort. And then we put little particles in the beam. And this is what we get. And this is from Dave Greer group at NYU, and they use a lot of this sort of beams for studies of colloidal solutions. Okay, so when the single particle interacts with the whole beam, it experiences a torque about the beam axis. Okay, so how can we do it all? So the simplest of ways is to do the following things. So again, I have my normal setup here, which I was showing you before. So I have my laser, shaping lenses, few mirrors, etc. High numerical aperture objective, etc. Light is going to CCD or to photodetector here. So partially to CCD, partially to photodetector. Now I introduce my mask, which when I put the Gaussian beam on it, on transmission, it will become Gauss-Laguerre beam. And in this case, what is drawn here is a mask which will produce charge 3, we call it. So it's L equal 3 h bar orbital angular momentum per photon. Okay? Okay, so here it is. So this is how this beam looks like. I showed you that before. Now, our first experiment a long time ago, again by accident, was done on an absorbing particle. Okay, so this is a highly absorbing particle, and the idea here was really to get this hollow beam so that you can trap the particle in the dark spot of the light. Because as you remember from the previous speaker, if you have a highly absorbing particle, then of course it will be pushed out of the most intense part of the beam. So here it would be pushed out of the ring of light, but it would be trapped in the middle of the dark spot. So that was the idea behind it. And when Howe did it, what happened was that the particle not only was trapped, although only two-dimensionally, but it was also rotating. And when he changed this helical beam from being right-handed to being left-handed, it's still linearly polarized. The particle changed rotation as well. So this was definitely transfer of orbital angular momentum of light. And so if you have absorbing particle, introducing energy onto it will heat it, and momentum will make it press against the slide, and angular momentum will make it rotate. So from the EM theory, we know that light carries momentum and angular momentum is scale. Okay, so if we look at the results from the rotating particles, this is what we got. So basically, again, what happened was that we sent the paper for publication, and nobody wanted to believe in the results we had. So we had to convince them by trapping the particle and rotating it in orbital angular momentum beam, and then saying, okay, if I now make this beam to be circularly polarized in the same sense as the orbital angular momentum is, then I will add 1 h bar, so the particle should speed up. And if I add to it a circularly polarized light in opposite sense, then the particle should slow down. And this is exactly what we saw. And it was in the proportion to what we were expecting, because we had orbital angular momentum light here with L equal to 3, and then +1 and -1 gives this result. So that was a real transfer of orbital angular momentum. And I think that I will stop here and continue tomorrow. So.
Questions, please? I have one. So, to generate the LG beam, do you use face mask or is it acting as a grating?
Well, we are using, it's holographic plate, basically. So we create it first as a mask, and then we make a hologram out of it, face hologram. But obviously, you can do it using SLMs. The only thing is that we sort of were sold on this method, not only because we started it, but because you can actually produce pretty perfect holograms doing it this way. And you can get very nice distribution of intensity of light, which is quite important for many applications, not only for optical tweezers, but for atom optics, which I also do, with phase singular fields. When you do SLM, now they're getting very good and you can do it, but there is a lot of playing with the algorithms which you need for producing good masks like that.
More questions? If not, let us thank our speaker again.